So Professor Choke just gave us a fantastic overview of nanophotonics. And now I'm going to talk about a little bit focused topic, which is plasmonics and the metamaterials. I think Professor Choke already mentioned a little bit about that part, but I'm trying to elaborate that and show you the fundamental physics and some other application of this plasmonics and the metamaterials. So let's just get in the point. So I'm going to talk about plasmonics and metamaterials. Plasmonic, this is exactly the same picture you have seen just a few minutes ago. So the plasmonics is basically, it's how do we use light to manipulate the movement of free electrons in metal, primarily metal materials. If we take gold or silver as example, each gold or silver atoms have one free electron, right? But you have gold crystals or silver crystals, you could possibly have many, many free electrons for us to manipulate. How do we manipulate it? We use light to excite the collective pattern movement of free electrons in metal materials. Okay, once you have a pattern or periodic pattern forms in terms of the electron movement, then you start to have something like a wave type of interactions between a photon and an electron wave. But in this case, this electron wave is not exactly as electron wave when we talk about quantum mechanics. Right here, the actual so-called electron wave is basically that electrons start to accumulate at some localized area. For example, here, let's say, in this metal, we have a lot more electrons accumulate right here. Then the other side effect is that you have some area short of electrons, so it becomes a positive charge equivalently. That's why you can have those periodic patterns of short of electrons or rich of electrons, and you have those positive charge and negative charge region form as a periodic structures on the surface of metal and the dielectric materials. So you can use light basically to create that kind of electron wave, but it's not exactly electron wave as we'll talk about in quantum mechanics. So once you have the wave like this, you can imagine that this wave can propagate along this interface between the metal and the dielectric materials. It can also be confined if you have any physical nanostructures. Okay, so this is the plasmonics. This is a very cool thing because this is probably what people can use external free space propagating wave, light wave, to manipulate hard free electrons in the materials to distribute basically or propagate. Okay, and if we extend that ideas, let's adding a little more materials to this plasmonic material. Here's only metals, but if we make this metal dielectric composite in the nanoscales, then we can basically create artificial materials that not existing in nature. Okay, that is the name for the metamaterials. The meta means it's not true. This is virtual materials. This is not a material you can find in nature. It's really something that you create by engineering methods. Okay, so typically the metamaterial we're talking about is made of constituents, is basically composite structures made of metals and dielectrics. So this is not a homogeneous materials. Basically, it's inhomogeneous artificial materials made of metal and dielectric materials. But because those metal and dielectric structures in these metamaterials are very, very small. They are actually much smaller than the wavelengths. So in the wavelength scales, we can effectively assume that is a homogeneous materials, but has very different physical properties in comparison to either metal or dielectric. So now we're creating a artificial materials made of and basically blending the metal and dielectric materials in a way that they can have your desired property. So we will start to talk about how do we make them and how, what's the property of those metamaterials. First of all, the application of plasmonics. Okay, again, this is a pretty much similar picture as the previous slides, showing that whenever you have a dielectric metal surface, possibly you can excite this collective electron movement that follows the the frequency of your excitation light wave. However, the wavelengths can be definitely controlled by the property of the metal as well as the structure of the metals. Okay? And so here is something we call SPP, or surface plasma polariton, which is basically a transverse EM wave. In this case, it's transverse wave that our E field is in plane, the E field inside the plane, and H field, the magnetic field, is perpendicular to this plane. So this transverse EM wave then coupled to a plasmon, okay, this wave is in the free space then coupled to this plasma and an interface of metal and dielectrics. And the wave of charges on the metal dielectric interface, and this is called surface plasma polariton. So basically it's a coupling effect between the EM wave and the free electron movement on the metal surfaces. So once you have, let's say this is probably in a very smooth surface. In this axis, we can assume this is the infinite long surface. So you could imagine we could have this propagating wave along this interface. But if you have a nanostructures, like if you have a three-dimensional gold or silver nanoparticles, then you can literally confine this wave within that physical boundary. That's exactly what happens here. Whenever you have a plasma wave trying to propagating, it will bump into the actual physical boundary of the nanostructures and come back. So you will literally creating a resonant cavity for that plasma wave. And once you confine that within the very small structures, you can see, you can basically define what is the resonance mode or resonant frequency of that, so you can control the actual resonance color or wavelength of that particles. Okay? You can also do this by using engineering method to create nanowire structures or create nanodots array structures, and by changing the three-dimensional structures or two-dimensional structures, you can basically tailor the actual resonance wavelength or frequency, so they exhibit different colors. Here's an example showing that this is an array of gold nanowires. They have the similar length, but they have different width. So if you excite this gold nanowires using a polarized light and with a polarization direction along the short axis, then you can excite the plasma resonance mode along the short axis of the nanowires. And because they have different width, so they have different plasma resonance mode, and so they can exhibit different colors in this kind of pictures, right? Well, we know that whenever you have electron oscillations, you could have the secondary radiation due to that electron oscillation. In this case, because the oscillation is either along this vertical direction or along the short axis, so that's so these structures can generate the secondary emitted light, which is also scattering light, and that basically have this exactly same frequency as a resonance frequency of the nanostructure. Okay, so this is Plasmonics examples. So if you look at the actual history of plasma research, this has been dated very long ago, back almost 70 years ago. This actually so-called surface plasma was discovered in 1950s actually. It's a very, very early discovery. But back then, since we don't have the engineering technologies to create this nanostructure or nanoscale devices, so for almost about 20 years period, there is very little advancement in terms of the plasma running research. However, since the actual people start to continuing improving the engineering manufacturing method and also discovering new materials, then you can see that people start to realize those plasma resonant devices more and more, and especially in the recent 10 years, in the past decades, you see this real explosion of this plasma mining research due to also the advancement of nanotechnologies. So especially in the recent 5 years that people start looking at, if we extend this plasmonic concept to make the composite of metal and dielectric material, make them into metamaterials, and how do we use that to realize some function that you can never realize using the natural materials. So if we compare the natural materials with the metamaterials, then we can see that for the metamaterials, we only need to use the classical waves to describe the physics about the metamaterials. That's a very good thing because you don't have to deal with Schrodinger equations at all. You can basically just rely on the classical EM theory to study the metamaterials. But for common natural material, because you are dealing with these atomic structures, so sometimes you do have to deal with the quantum mechanical theories. For constituents, for the natural materials, typically is made of array of atoms into a crystals, right? But for metamaterials, we're not yet down to the atomic level yet. We basically are still relying on the molecular levels, or let's say nanoscale levels. So basically you have to, as long as you have ability to create a structured metal and dielectric materials, you can always engineering two-dimensional or three-dimensional structure with a composite of metal and dielectric, and then you can create the so-called metamaterials. So we're not get down to the atomic level for the metamaterials. In terms of geometrical variants, of course, if you're talking about natural materials, we're talking about there's a lot of crystal orientation and crystal lattice shape. But for the metamaterials, basically, this is engineering materials. This is not defined by nature. So we can always engineer it in a way, in a very perfect way that we can always design it in our computer and using nanofabrication tool to design our exactly the actual shape you want. So that's these two properties makes the metamaterials even more attractive than the natural materials because everything is controlled by human being here in terms of structures, in terms of the actual shapes. But for the natural materials, we basically lose the controllability for atomic structures and also crystal structures. And in terms of dopant or defect, that's actually even better for the metamaterials, that we can use engineering method to control the dopants or defects in the metamaterials. But in natural materials you find in nature, typically those dopant or defects are random. Okay, so the metamaterials basically is a materials with very strange, very different properties. In this case, we will limit the actual discussion of metamaterials in the scope of electromagnetics. Okay, so here we want to discuss about particularly two important parameters about the materials. One is the electrical permittivity. Another one is magnetic permeabilities. Okay, basically is epsilon or mu. Okay, so by engineering the material property or by engineering the actual material composition and the structures, we can engineer the epsilon and mu. If you take any natural materials, those epsilon and mu are already defined by God, right? But if we engineer these metamaterials, we can be a God, and we can really define the epsilon and mu as we want. So that's why we have a lot of room to play with for these metamaterials, well, especially in electromagnetics. For the metamaterials, we have looked at the fields of individual nanostructures, okay, to study how the electromagnetic fields distribute within that structures. And also we have to look at the sub-wavelength scales to see what is the effective medium limit. Okay, and we also have to look at the resonant response of that materials to the electric or magnetic fields. Okay. And so it's possible for us, if we choose the material correctly, if we choose the composition and the arrangement of a metal and dielectric, for example, you can always choose 80% of metal, 20% of dielectric, or 30% of metal, 70% of dielectric materials. You can construct them in a very special way, and if you do that well, you can always, it's possible to design a metamaterials with a magnetic response or electric response at optical frequency that no natural materials can exhibit. Okay. For example, we can create something called a negative refractive index materials, okay, which is not existing in nature. You cannot find any material in nature has negative refractive index. So all the N, or the actual refractive index N for the natural materials are all positive. Okay, that is why, you know, this is the normal material. For example, if you have a concave lens made of a normal dielectric materials, you would expect you have, you know, this is a light source. If you have a light source, slightly diverging beam passing through this concave lens, if this lens is made of natural materials with a positive refractive index, you would expect they have a further divergence of this beam. However, if you have a lens made of this metamaterials, which is artificial material, with the negative refractive index, instead of diverging, you will see a convergence of the beam or focus on the beam passing through this concave lens. Okay, concave lens. Or another example is if you made some liquid which has has a negative refractive index, what you will see, well, if you have a spoon or a straw insert into the water, instead of seeing something like this, you would actually observe that the actual straw or the spoon underneath the water will have this kind of weird behavior, which shows an exactly opposite direction as this part outside the water. Okay, so well, imagine that you have the liquid which has a refractive index that is negative. So the application, definitely, there's a huge application. If we can create a metamaterials with a negative refractive index, then we can do a lot of detections, switching, modulations of light, and create engineered birefringence of light. Okay, create a material with the engineered birefringence. So here, an example showing there's some metamaterial people have created using the composite. Using the composition, using the combination of a metal and a dielectric material. So here, I believe those are copper rings, copper ring arrays made into a three-dimensional plastic scaffold. So this is basically three-dimensional metamaterial. This is two-dimensional, and these two materials has negative refractive index. In this case, they have negative refractive index in a microwave frequency region. Okay, so if you have a microwave passing through this material, instead of having a positive, instead of having a divergence in the beam, then you have convergence in the beam or focus in the beam. Okay, and one other example of people showing that even just by using a very simple thin film of gold or silver, you can then focus in the light without using any lens structures. So here's an example showing that if you have a point light source on the left-hand side of this metamaterials, and once this light beam wave pass through this and get into this metamaterials, this wave will become focused or diverge or focus in one point, so you can have an intermediate focusing point or image forming within the metamaterials, and then in the end you can have another imaging forming at the other side, at the right hand side of these metamaterials. This is not possible for any natural materials. Well, imagine that if you have a piece of a glass or just a simple very small let's say if you have any thin layer of plastics or glass materials, and you would have imaging forming, or you will not have any imaging forming if you have a point source at one side of this film. All right. So this has been demonstrated in experiment that when people placing a nanostructure point source, which is this case, which is the pattern of nano, placing on the right-hand side of this metamaterials, and they're trying to image this object from the outer side of this metamaterials without any lens. Okay, this is basically you are imaging a object, a point source, without the actual lens. This is completely a flat surface. Okay, but you can still form imaging at the other hand because now you have so-called negative refract index that can basically bend the light in very different ways. All right, so if we try to define or classify the media depending on their epsilon and mu, we can always define the actual materials into different categories. But before that, let's give a very, very quick overview or review of electromagnetic waves in the media. So this is the Maxwell equation, source-free Maxwell equations in the media, and then we have the electrical displacement, we have electric field, and we have magnetic field B and H. Okay, and we can relate the D with E and B with H by their permittivity and the permeability. And so when we design metamaterials, basically we have to look at these two particular parameters, epsilon and mu, relative permittivity and permeabilities. And by manipulating the actual material properties, we can then have very different epsilon and mu. So we define that by this basically four quadrant here. In the first quadrant, that you have positive epsilon and positive mu. So that is a materials called a double positive materials, and all dielectric or natural dielectric materials are double positive materials, or DPS materials. So they have a positive epsilon and a positive mu. And if you have electromagnetic waves propagating in that kind of materials, you will see a propagating wave with a very little loss or the attenuations. But if you have a metal materials, the actual natural metal typically has a negative refract epsilon and a positive mu. So that's called epsilon negative materials for the metals. If you have magnetic wave propagating in the metals, you will see a lot of loss and also a very, very huge attenuation. That's why when we discuss about metal in the classical electromagnetics, we always discuss about skin depth of metal because we know that actually the waves will attenuate a lot into the metamaterials. So the actual skin depth for most electromagnetic waves is very, very small. So then let's discuss something that's not found in nature, which is something we want to create for the metamaterials. That is double negative materials, which have both negative epsilon and mu. So epsilon is negative and mu is negative. Okay. In this case, you could also have propagating wave. That's very very exciting. So we can expect there is electromagnetic wave propagating with very little loss in that materials. However, that material is not existing in nature. So we have to use engineering method to create that materials. Okay. Well, there's another materials which is mu negative materials, and it's also attenuating because in this case you have a huge attenuation for the magnetic field. In this case you have a huge attenuation for the electric field. So now let's keep our eyes on this double negative materials with epsilon less than 0 and mu less than 0, small and zeros. Okay, if we have that materials, what we would expect is we can have something like this. Okay, for a normal electromagnetic wave propagating, for example, in the dielectric materials, and then you would expect the phase velocity and the group velocity will have the same sign. We have the same sign, which means if you multiply the phase velocity with the group velocity, you can have a value which is larger than 0. But if you have a metamaterials with double negativity, then it's possible that you can have your phase velocity and group velocity has a completely opposite direction, which means your energy flow has the opposite direction of your wave vectors. So that's, sounds a little bit mind-boggling, because in a very conventional way, when a wave propagates, it will also carry out the energy flow with it in the same direction. But for the electromagnetic wave propagating in the metamaterials, your energy flow will have opposite direction as your wave vectors of your, as your wave numbers or your wave vectors. If that's the case, we would expect something called negative refraction. Negative refractions. In this case, for example, for the positive refractions that you have, which is for the first case, that is the case for the positive refraction. And then when your electromagnetic waves propagating from air to the media, okay, to the glass or other dielectric materials, you keep the same K vectors, and of course, this K vector has modified depending on the refract index. But your K vectors have the same direction as your energy velocities. So your S, your pointing vector S, has the same vector, has the same direction as your K, as your wave vectors. This is for the positive refraction. This is true for any lens, concave or convex lens made of glass. This is always true, which is a positive refraction. But if we have metamaterials with negative permittivity and permeability, then what we will see is once the wave propagating into that materials, your pointing vector S will have the opposite direction as your K. So in the end, if you have a wave propagating into that directions, then after this wave getting into this metamaterials, the wave will be bended to the opposite directions. For any refraction to happen, you would expect your wave will stay at this, well, for example, if your wave is actually impinging from the left-hand side of this normal lines, you would expect for the positive refraction that refracted wave or beam or light will remain on the right-hand side. But in this case, for the negative refraction, that wave is really bent to the opposite direction. Okay. This only happens when you have negative refract index or double negativity materials. So here I just get some example from the internet that people have done natural simulations for if you have a metamaterials, what the magnetic negative refraction will look like. Okay, so here we have a thin slab of metamaterials with negative mu and epsilon. For the normal refraction, you would expect that if you light a propagating, well, this is a plane wave propagating in the air, then getting into that piece of positive materials, and you will see the wave will be bending in that direction. But for the negative refraction, your wave is actually bent to the opposite directions. That's why you will see the wave is really bending in a very different way. And this is the case. This is the case that. Showing that if we have this metamaterials with double negativity, both epsilon and mu are negative, then if you have a point source at one side of these metamaterials, then you would expect there is a point image forming at the opposite side. Okay, this is not possible at all for a normal materials. If you have a natural materials, you would expect this point source will definitely have this propagating spherical wave propagating away from the point source, and that wave will continue to propagate, and you have no way for an image forming in that case. Okay. Sorry, it's not willing to go. Yeah. All right, so if we have that, we can also have other benefits. If we have these negative mu and epsilon, we can have another benefit, which is we can break the diffraction limit of our image. Whenever we do optical imaging, we are bounded by the diffraction limit, which is the actual limit in the highest spatial frequency that we can use our optical imaging system to detect. Okay. So, so this is a case showing that in a K space, which is frequency, which is a spatial frequency space, or in this case, wave vector space. For normal or for conventional optical imaging systems, we're limited by the upper boundary, that's the diffraction limit. So for the spatial frequency lower than that limit, we can see that clearly. But if you have a spatial frequency higher than that limit, we cannot see them. Okay, so here is showing that before filtering of that case, this is a very, very sharp, crispy image with a lot of high spatial frequency components. But if you filter out those high spatial, high K space components, and you will see a very blurred image. That is because all this high spatial frequency has been filtered out. So that's a typical case when we're trying to see something really small. Because if we're trying to see something small, we're limited by the spatial frequency limit. Now we can only see a very blurred image. If we can keep increasing that limit, and then we can have a higher spatial frequency components can be acquired by the optical imaging systems. This is exactly why we want to use metamaterials to do that. Okay. In a conventional lens, the conventional lens can only focus the propagating wave when this wave vector K, or wave number, is less than omega divided by C. Okay. Or you can translate that into diffraction limit. The resolution for the diffraction limit of optical imaging systems is about quarter of wavelengths. There's no way to get beyond that for conventional lens systems. However, now we're trying to create a K that is a lot of smaller than the actual K in the free space or in the natural dielectric materials. If we can have a K a lot smaller, then we could have this diffraction limit has been brought to the actual higher limit. Well, here I want to correct this. Actually, we want to squeeze the wavelengths, but we want to improve the K in the plasmonic and the metamaterials so that we can bring this limit to higher levels. That if this is a maximum, if omega over C is the maximum K we can see, then we want to bring that up so that we can see even higher spatial frequency components. And that is a concept for a plasmonic or metamaterial super lens device. So here is showing you what is happening in the actual materials. Okay, when you have a K vector, which is spatial frequency or wave number or wave vectors, larger than omega over C. Okay, this is for the actual natural materials, and you will see a evanescent wave in that materials or a decaying wave. But if you have a K values less than that, lower than the limit, then you will have a propagating wave with very little loss. Okay, so this is what typically happens when you have a very high K values in your optical informations. That's why we cannot see those information from the other side of this of the lens. But now, if we have this negative metamaterials, then we can have a space with a lot of higher limits, so we can allow a higher K components to pass through that materials. Okay, here showing you the exactly same thing that I'm showing you in that videos. If you have a point source passing through that materials, you can form image at the opposite side of it. Okay, all right. Then how do we improve that K? How to improve that K? So I should have slides following this one. Okay, but before I talk about that, let's go through some mathematics about surface plasmonics. Okay, because this metamaterials basically is the extension of plasmonics, because you would need to have the metal in your metamaterials. So let's start to discuss about the plasmonics. For the plasmonics, we can use the simplest Drude model to explain it. Okay, this is very simple motion of electronic models. Okay, if you have, this is basically a kinetic energy of your electrons, and this is your electric field and charge of your particles, and that equation can be translated into this. Okay, and then you can include the angular frequency, omega in this case, and then you can further write this equation as this polarizability P as a function of the x. X is actual movement or displacement of your free electrons in the metals. Okay, that's definitely related to your electric field and charge, and here your angular frequencies. So if we have that expressions, and if we also use the actual Maxwell equations, then what we have is the relationship between the permittivity or dielectric constant epsilon with the with angular frequency omega. So here, for all the plasmonic structures or plasmonic devices, our epsilon equals 1 minus omega p squared divided by omega squared. Here, omega p is so-called bulk plasma frequency. That is determined by the free electron density n and the charge of 1 electrons and the electron mass and the permittivity of vacuum. Okay, so this is basically a constant for given materials because we know what will be the free electron density for any metals, either gold or silver. We will know this number m. Once we know that, we will know the plasma frequency. If we know the plasma frequency, then the actual permittivity becomes a function of your frequencies. Okay, you can vary frequency. For example, your frequency, well here of course is 2 pi f, right? This is 2 pi f. This is so-called angular frequencies. But if we talk about frequencies for a let's say for a visible light, it's 1,000 of terahertz. Okay, 1,000 terahertz. So you can see that if you vary the color of your light, your frequency, your omega will change, then your epsilon will also change with it. So this is not a constant value. Your epsilon is a function of your light wavelengths or frequencies. That's important because that will give the materials have different properties at different wavelengths. That's exactly why you only see the plasma resonance as some color but not the other colors because of this. Because their permittivity is not constant, but a function of the frequencies. All right, so if you have the plasma happens, what will happen for the K values? This comes back to the K, right? You know, for a wave propagating in the natural materials or in the dielectric materials, this is the K you would expect. Okay? Your K is linearly proportional to your angular frequency omega. So your omega K, this is called so-called dispersion plots. That is a plot, the relationship between omega and K. You would expect you have a linear relationship between omega and K for your dielectric materials. But if you have a superplasma wave, then your K becomes something like this, which means for the same frequency, okay, for the same frequency, let's say if we look at this frequency, omega p divided by square root of 2. In the actual, in air or in the dielectric materials, you would have a K value like this, right? This is your K values. But if you have a superplasma, for the same frequency, then your K value is much greater. What does that mean? That means this plasma wave allows higher spatial frequency or higher wave factor to propagate in that material. That's exactly what we want, to have a superlens to allow higher K vectors or higher spatial frequency vectors to propagate in that materials. So here the red curve is the K is so-called dispersion relationship for the plasmonic waves. That is modified from this one is omega c times this particular term, and this term because then you have epsilon here, and the epsilon is a function of the frequency. So this K value is a function of frequency as well. That's why you see that this is not a linear relationship, but a nonlinear relationship.
One question.
Yes.
Does it really take the value, or is it an asymptotic relation?
Does it take the value?
Is it an asymptotic relationship, or because it looks like it really approaches that value?
Oh, well, this is basically, yeah, this is
the K values are on the opposite, right?
Yeah, yes, this is K value. This is omega.
Yes, but I'm just saying the red curve, is it asymptotically approaching the omega p dividing square root 2, or is it?
Yes, well, for this case, yes, that's the case. Your plasmonic, your dispersion relationship will reach to that limit, to that limit. But this is not the case for other nanostructure plasmonic case. This is only for this thin film surface plasma wave. And if you have a localized surface plasma case, then your wave is basically confined with the physical boundary of either two-dimensional or three-dimensional structure like this. Then you have to modify the equations. Then your plasma resonant frequency, or even your bulk plasma frequency, has to be modified depending on the modes number of that plasma resonance in that three-dimensional structure. For example, in the spheres, if you look at this fundamental mode, which is a dipole mode, and you have to make the L equals to 1 here. L is a mode number, okay? If you make the mode number equal to 1, then your dipole resonance frequency in a sphere equals to omega equals to omega p divided by square root of 3. And here is a slide showing you the comparison between the surface plasma resonance and localized plasma resonance. I will not go through the detail of each equation here, but you can see here is what you get the slides, so you can basically use those equations to analytically solve the dielectric constant and to find out the resonance mode or resonance frequency for this for the surface plasma and for the localized plasma resonance. And so then people, thought about if you have this plasmonic wave in different modes, you can possibly make them into so-called optical antenna, right? Because then you can use the nanostructures to dictate what kind of a field patterns is. For example, the simplest case is a dipole mode. There's an actual electric dipole. You can create a plasmonic dipole. You can create on the simple metal nanosphere or nanoparticles. If you have that, you would expect those kind of a dipolar pattern, radiation patterns from these particles. And then if you create, for example, this nano bow tie structure made of these plasmonic structures, you can then, instead of having this one, you can have a focusing of light field or EM field between these two tips of these nano bow ties, and then create locally much higher electric fields in this particular regions. Okay, in this particular region. So for the quasi-static approximation case, to achieve this dipolar resonance, that is the relationship you have to satisfy. Then this requires, when for this metamaterials, your dielectric constant has to be equals to minus 2 epsilon h. Here, this epsilon h is a permittivity of the dielectric media. That means the permittivity of this dielectric media or dielectric media surrounding these particles. So for the resonance, for dipolar resonance to happen, this condition has to be satisfied. Okay, so your real part of your permittivity equals to minus 2 times epsilon dielectric constant, the actual dielectric material surrounding the metals, and your imaginary part of epsilon has to be close to 0 in this case.
Question?
Yes.
So, can you go a slide back, or 2 slides? Yeah. So, what's the difference here between these 2 descriptions here of localized plasma resonance and surface plasma?
Oh yeah. So for the surface plasma resonance, we are trying to solve the wave propagating along the interface of dielectric materials and the metal. But here we're trying to solve the wave that is confined within the metal nanoparticles. Okay, and here this is basically very similar to our solving in this case. Okay, But for the nanoparticle case, I'm giving an equation that you should modify the dipole moment depending on the size of the particle. For example, depending on the radius of the nanoparticles here. So here it has nothing to do with the actual dimensions of the actual materials. There's no dimension term here. But when you have a three-dimensional nanostructure confinement, and you have to consider the actual dimension of that structure. That's why if you have different size of particle, let's say 20 nanometer or 50 nanometer or 100 nanometers, your plasma resonance mode will be different. That has been modified by including those size parameter in there. So those equations that give you, for you to calculate that plasma resonance mode in that particular particle.
Is this still a classical?
This is still classical, yes. Still classical.
And the effect of the surface plasmon oscillations, is that also a classical effect, or is this are the oscillations quantized? Because I would, like when you wrote down the levels of P, look like only parameters that depend on the.
Yes. Well, this right.
So this is a quantum mechanical effect? No,
well, this is not exactly the same as quantum mechanics, but people do use quantum plasmonic to define these modes because this equation really looks like quantum mechanical modes. You have discretized mode in its plasma resonance, but this is not due to the electrons, your core electrons jump into different energy levels in your atoms. This is really due to that your free electrons in your metal has been moved in a pattern way, in actual periodic ways that's confined by the actual geometry and also defined by your excitation light. Okay, this is a this is actually two very different concepts. One is regarding to the electron bonded to the nucleus has been jumped into different energy levels in the atoms. Okay, but here, this is always a free electron, freely moved in that materials, but it has been basically guided in a way that moves in a very periodic or in very pattern ways, and that pattern is defined by the resonance mode here. Okay. All right, so the people do use this for a sensing application. For example, people have demonstrated you have a nanoparticle localized localized plasma resonance. Then you would expect the actual resonance peak, wavelength peak, is related to the refract index of the media surrounding that particles. And then by changing the actual media from this is actually the particle in the air. If you change that media to water, then you can see there is a huge shift of the plasma resonance mode. And if you change that refract index a little bit by adding different DNA or proteins on the surface, you can further modify that refract index. Then you would expect there is some other tiny shift of the resonance mode. Okay. So this is the applications of that, and we will have a session about an application in the next week. And the people also use that, if you use the plasmonics to manipulate the electric field, you can create a very high localized field that allow you to enhance the vibrational spectrum of molecules. So because of time, I will skip this part. And then move on to design of the actual metamaterials. So if we want to design metamaterials, we have to use both metal and dielectric. But there's also some rules we have to follow when we design metamaterials. We cannot just randomly to design any materials, because for a metamaterials, even for the metamaterial, it has to follow so-called causality, which is defined by this Kronig-Kramer relationship between the real part and an imaginary part of your dielectric constant. Well, here is we basically use chi, which is electron affinity. Chi is the function is related to your effective epsilon, your effective permittivity. Okay, epsilon effective is the effective permittivity of the metamaterials. That is very different from the permittivity in the natural materials. So chi equals epsilon minus 1. So the chi relationship, the chi has to satisfy this Kronig-Kramer relationship, which your real part and the imaginary part of chi has basically entangled together. This has to be satisfied even for a metamaterial. Once you have that relationship satisfied, and then you can start to design your metamaterials. Again, here we want to design something in this quadrant, which has negative permittivity and negative permeability. Okay, so to have that, what we want to have to do is for the natural metal, it actually already exhibits a negative epsilon at optical frequencies. So what we want to do is we want to blend this metal with the dielectric together so that we can not only have the negative epsilon, we also can have the negative mu at the same time. So, and then of course people also find a very different way to try to lower the plasma frequency. For example, you can either dilute the electron density, or you can either by applying very high magnetic fields to equivalently increase the effective mass of electrons. If you do that, then you could basically increase or lower the actual plasma frequency of the metamaterials. And then if you add the dielectric into metal together, something like this, okay, and then you can create some metamaterials with different mu and different epsilon. The simplest way to create metamaterial is to stacking metal and the dielectric materials alternatively. Okay, here is a multi-layer stacking structures between metal and a semiconductor. For example, you can treat this light blue as metal and this dark blue as dielectric materials. If you stack them together like this, and you can equivalently create a material with effective refractive index or the effective permittivity that is different from metal from metal and the dielectric materials. Here, the result is the effective permittivity equals to F. F is so-called fraction numbers. The fraction numbers is defined by what is the proportions of, in this case, metal in that metamaterials. For example, if you have 50% metal and a 50% dielectric, then your F number should be 0.5, right? And so here, by using this composite material, you can constitute a artificial material with an artificial effective permittivity epsilon. And then you can basically to design the epsilon that is also a function of frequencies, okay? Function of frequency. And there's another way to make it, and people have created this so-called split ring array and to create the negative permeabilities. For the natural magnetism, we have to use the left-hand rule to basically find out the actual B field. But if you have this structure made, then your B field basically is the opposite direction compared to the natural magnetic fields. So in this case, then we will have a negative mu. That is exactly the actual region we have to look at. Here, in this particular region, we have negative mu right here. This is created by creating this array of splitting ring made of metals. And what our people have also demonstrated is making this so-called split ring arrays out of metals and then using dielectric material as a spacer layers to create the three-dimensional arrays. And then this material will have both negative epsilon and a mu. Okay, here in this region, you would have negative a mu and a negative epsilon. Okay. If you have a negative mu and epsilon, then you would have very nice metamaterial to allow you to do negative refractions. So that's why people can use this. The plastic, which people use to make a PCB, print circuit board, and print some copper split ring on the surface and construct that into a three-dimensional circuit board. Then people and then place that device on top of this sample holders. And then if you have a microwave source passing through this sample, what you will see is instead of having a positive refraction, let's say, if you have a microwave propagating along this direction, for a normal material, for natural materials, you would expect, well, this is a normal line, okay? You would expect your refraction will follow this kind of directions. This is called a positive refraction. But instead of that, they have measured the so-called left hand or the negative refraction by measuring the actual refraction at these angles, okay? At these angles. So they're actual results. This is the actual positive refraction, which is Teflon case. But for these materials, you would expect to see this kind of refraction patterns measured at very different angles. This is another example. By using this multi-layer stacking structures, you can create so-called metal dielectric metal or metal insulated metal, MIM. Fissionized structure can realize the near optical frequency negative refractions. Due to the time issues, I will just directly jump into the actual diffraction limit case. This example is showing that if you have this thin film of silver, then you can basically transfer that nanostructures to the outer side of the thin film of silver. Okay, so basically you are forming a image without using actual lens. You can also do this in the far field by creating this multi-layer stacking structures. You have a metal and dielectric alternating structures and bend them into a curve so that those nano patterns can be transferred to the far field case. This is actually a very nice demonstration. You can use these things to transfer the nanostructures into the far field without a lot of distortion and diffractions. And this is not possible to do that before, okay? And this really breaks the diffraction limits and bring up that frequency, that so-called spatial frequencies to a higher limit. All right, so, and here I want to conclude my talk by give you some outlooks. And one hot topic now is so-called metamaterial cloaking. That's what people always try and, dream about. You can have a very magic cloaking poncho that once you wear that and nobody can see you. This is because you are playing a trick on the light wave. If you have that materials, basically all the light wave will be bended and go around it, but eventually come back to the original wavefront or wave shapes. So this is actually in the actual simulation, people already predict that can happen. If you find a way to engineer a material or device with this kind of permittivity and permittivity relationship, this case is that your epsilon mu is a function of the radius. So this is not a homogeneous materials. This will be a very inhomogeneous materials, and this relationship you have to satisfy. But once you have this relationship satisfied, when the wave, electromagnetic wave passing through this, it will just go around it as if there's nothing over there. And if you see from this side, you will see directly what you see over here. So you will not see anything in between. That means this object has been cloaked effectively. Okay. But people are trying to make that in optical frequencies. So now people already demonstrate they can do that in optical frequencies. So this is a recent demonstration that you can do the cloaking device by using the actual metamaterials. If you have basically just a very simple mirror, you would expect for a plane wave propagating in these angles, you will see a plane wave also reflected from this mirror surface. But if you have a bump on that mirrors, you will see basically a divergence or a distortion of the wave, like that, right? But if you add a metamaterial device on top of this bump. Well, this bump can be, say, can be a single living cells or some other dielectric nanostructures or microstructures. But if you cover that structures with the actual metamaterials, you will see that the wave is reflected in a very similar way as if there's nothing there. So for people observing from this angle, they will not see this object at all. Okay. For this case, if you have a person standing there, they will see there's a bump there because the bump really changed the condition for the light refraction. But for this case, because all the wave is banded back in the same way as before, as if there's nothing there. So what people perceive outside is there's nothing really covered underneath it. Okay, so people have demonstrated in optical frequency to demonstrate this optical cloaking. So if, let's say, if you have one tiny microorganism, or you have one tiny little person hiding in these regions, and that person cannot be seen by the actual observer outside these regions.
Is this effect inherently at a very small scale? Is it scale dependent? Because I've only seen this effect like demonstrated in small metallic microspheres.
Yes, because there's some pragmatic issues. If you want to make a really cloaking device working in a human size or in a large object size, you have to make really big metamaterial device. And also, if you get to that big scales, then your physics may not work, especially on the boundary case. Okay, and there's a lot of practical issues. That's why people only now demonstrating the actual cloaking in a microstructure scales. That's actually the current status. But I think in a few years, people try to make it bigger and bigger. Maybe eventually try to cloak millimeter scales, or eventually to really large scale devices.
So the limitations are not engineering. They're not physical. You're saying they're just engineering right now.
Yes. Right.
Oh, okay.
Yeah. All right. As a conclusion, I will talk about plasmonics and the metamaterials. Definitely, there's a very complicated concept involving this one, and you can go back to digest the actual slides. And another overlook is, of course, Professor Choquet already gave this overlook that you can use this plasmonic and the metamaterial structure to create some kind of extraordinary optical transparency, and you can also create nonlinear effect and some sub-wavelength wave guiding structure. All right, until now I will conclude my talk, and there's a few questions you can ask. I'm going to run out of time.
All right, thank you very much for a very interesting talk. Any other questions? Yep.
So in the experimental setups that you described for these negative epsilon negative mu materials, are they isotropic, like with regard to directionality?
Well, they're not isotropic. It really depends on the way that you create it. Well, for example, let's use that simple so-called multi-layer stacking structures, and your wave vector has to be perpendicular to these layers. If you have other wave penetrating, propagating in the other K vectors, then you will not have this property at all.
So in that case, if you want to use it for lensing, where you'll have multiple angles, do you have to have an isotropic material, or can you somehow get away with this kind of stuff?
So for the lens effect, yes. So your wave has to be propagated from these directions. If your wave is propagating from other directions, this may not work that well. It's because all the property has to be modified. So this is so far as metamaterials only works for a very limited range of frequency or wavelengths, and also only works for very limited range of K vectors. Okay.
Other questions?
But going back to the nanoplasmonic surface enhanced plasmon resonance effects you talked about. So I mean, you described, okay, you had these two descriptions, right? One that's dielectric. So you have these two descriptions that are in parallel. Yeah, the one about that.
This one?
That one. So you have surface plasmon resonance you're describing like with this classic electromagnetic wave that's being coupled with the surface plasmon oscillations, right?
Yes.
And so you can extrapolate that in principle, physically, to this picture here on the surface of your metallic nanostructure, right? In principle, or no? Because you say that this is on the right side. You have this localized plasmon resonance description. That depends on depends on the scale, depends on the size, right?
Yes.
So, to what point can you extrapolate, and at what point do you have to so at A you keep on scaling down, and you can't. So at what point does this classical Maxwell equation description break down, and you have to use more like quantum electrodynamics and like photon electron?
Yeah, that's actually a very good questions.
Like
so this
10 nanometers, you have like a few, maybe hundreds of atoms.
Right. So this actually is all based on Drude models. The Drude model is assuming your particle is much smaller than the wavelengths, much smaller than the actual than the wavelengths, but not that small. Not as small as get down to a few atoms or something like that. So typically we're talking about, if we're looking at the actual visible wavelengths, we're talking about from 20 nanometer to hundreds of nanometer to 100 nanometer. So that's a scale we're talking about when we apply this Drude model. Yeah. So if you have some particle or structure beyond that range, then this Drude model does not hold that well. Okay. Yeah.
So it seemed like nonlinear effects of these gold nanoparticle that they have to describe, using quantum electrodynamics and stuff.
Yeah, here we're not using any quantum mechanics to describe because we're still not getting down to any interaction between a nucleus and electrons. Here we solely discussing about free electrons in the metals.
So it's studying bulk. It's like you're kind of like leaving aside like the electron-photon interactions directly. So kind of bulk classical effects.
Right. Here we have to consider this bulk plasma frequency, omega p here. But because you also have different boundary conditions, and that boundary condition further modify the actual plasma resonance property. Well, if you have a thin film, let's say with very, very big scales, and that would be, and then you have air in that, then this actual plasma resonance frequency would be very close to the bulk plasma frequency, omega naught or p. Yeah.
All right. Well, thank you very much. Again, let's thank our